Hello everyone, welcome to Landscapes Fashioned by Water A, or Part 1, because it's just around the river bend. Okay, so as we learned with oceans, water can create landscapes due to its powerful erosional effects, such as grinding away rocks at cliff sides or moving and changing shorelines. The same happens with rivers, streams, and floods. The internal processes that we have are powered through energy from the Earth's interior. For example, geysers and hot springs. Okay, and then we have external power, where you have basically solar power. Everything's powered by the sun. So there are three major processes attributed to externals, which is weathering, which we know as the decomposition of rock, mass wasting, or the transfer of rock and soil downslope under the influence of gravity, such as slump, and then there's erosion, which is a physical removal of material by a mobile agent, whether it be water or wind, which is basically making sediments, which forms sedimentary rocks. So mass wasting has to do with the movement of sediment. It doesn't actually have anything to do with the wasting away of your body, which a lot of people think of when they hear mass wasting. So contrary to what flat earthers feel, the earth is not flat. If it were, the cats would have knocked everything out already. But it's not. It's actually covered with unstable slopes, which gravity causes movement on these said slopes to move downhill. And this is slow and imperceptible. We still have a lot of damage or catastrophic occurrences that happen from these slow, imperceptible movements, because while they are slow and imperceptible now, one day we're going to be like, oh my God, the mountain just fell down. Or, oh my God, my house just got destroyed by this slump that somehow has slowly been happening over the past few months, but no one has noticed. So it doesn't require a transportation medium like erosion does, or weathering. It doesn't require the necessity of water or anything else. What it has is gravity. And so examples of mass wasting is slump, avalanches or rock slides, debris flows, and earth flows. So this is an example of each of them. So here we have slump. Okay, so slump is the downward sliding of a mass of rock or unconsolidated material moving as a unit along a curved surface. So basically you have a hill. We have our hill. Okay, and on here we have unconsolidated material. Unconsolidated meaning we have big pieces and little pieces all together. They're not sorted at all. Okay, and because of this, it's easy for stuff to start moving. So what you'll have is a slow movement of everything starting to go downhill, which means you'll kind of lose this as this just goes down to the bottom like that. Rock slides are a bit more fast. A lot of times when you go north, when you go along the mountains, you'll see like netting on the side of the road, or occasionally you'll see big bolts. That is the county or state's way of trying to prevent a rock slide. And what that means is you just have all this rock that eventually, because of weathering, breaks off and kind of just falls downhill. This is pretty bad, especially if you're driving and all of a sudden a boulder comes out of nowhere and tries to destroy your life. In many of these places, you'll have signs that say, caution falling rock, or look out for falling rock, which has a Native American story behind it, which is kind of sad, but... And then we have debris flows. And debris flows is a flow of weathered debris containing a large amount of water. This is one of the few mass wasting types that involve water. And it doesn't even need a lot of water, it just needs a little bit. Again, we have unconsolidated stuff. Once some water gets in there, it reduces the amount of friction necessary that keeps it from moving, and it just starts to go. Often they go through channels that are already there, such as old riverbeds, and oftentimes these will be known as a mud flow. Okay, and then we have earth flows. So earth flows is a tongue-like flow of water-saturated clay-rich soil on a hillside that breaks away and moves downslope. Okay, so this is different from a mud flow or a debris flow. Okay, debris flows will have large amounts of water. So let's do this. Okay, large amounts of water. Okay, we need large amounts of water. Here we just have to have saturated. Okay, meaning saturated meaning think of a sponge. Once the sponge is oversaturated, it can't hold any more water. So we're not oversaturated. We just have water between every single one of these pebbles. Okay. This one's confined to channels. This one is not confined. Okay. These are your major differences between the two, other than how they look. One's also generally on a steeper slope and the other one is on a hillside. And you can see it looks like it kind of sinks and it just kind of goes along. This one's very fast. Okay, it's just kind of like a lahar. Okay, so how does this have to do with water? Other than the fact that debris flows and earth flows have water involved in them, over time, mass wasting will turn a rough, rugged, and steep landscape into a gentle, subdued terrain. Landform evolution has to do with weathering, breaking these rocks apart, mass wasting, transferring materials down slope, erosion then carries them away, and then sediment eventually gets to the seashore or the ocean. So how does it have to do with water? It forms stream valleys. These are the most common landform, and they are wider than their depth. So when you have a steep valley, like a V-shaped valley, mass wasting will widen said valley. So instead of it being a narrow stream bed, it'll become a wide stream bed. So here's an example that we all know. It's the Grand Canyon. This is a wonderful example of, we can see down here that the stream bed itself is actually quite narrow. It's a V. And what has happened is that mass wasting has caused it to actually widen over time. So triggers. Triggers are very important for mass wasting because there's this thing called friction. And as we all know, friction keeps us from just sliding along the earth when we walk. We stop when we stop walking, we go when we start walking, right? Physics. We all know, or I hope we all have been ice skating at some point. There are places around here that do it. When you are ice skating, you have less friction because of the way ice is. So you actually move pretty nicely, but you eventually do slow and stop. So mass wasting doesn't just magically happen. It actually has to do with gravity, which means that gravity needs to be greater than friction. In order for it to happen, gravity must become greater than friction. And the only way this will happen is if something causes it. Okay, so inertia is what prevents the evil plan from occurring, and gravity wants to get to destroy inertia, so you have to have something that triggers it, like on a gun. Okay, bullets just don't fire off on their own unless you have done something to them. So triggers include saturation, which has to do with how much water is in a material. So if it is, think of a dry sponge that is desaturated, a wet sponge, it's a regular sponge, but when you add too much water and it becomes saturated and oversaturated, it cannot hold it anymore and it starts to leak. Another example is bread. If you oversaturate bread, it falls apart. That's exactly what happens with mass wasting. So this is because water in pore space reduces cohesion and allows for particles to slide. Water also adds additional weight to the sediments, which allows gravity to become greater than friction. Okay, and then we have oversteepening. So oversteepening occurs when unconsolidated sediment, remember all the different sizes together, they don't exactly fit together. Unconsolidated sediment, okay? forms a stable slope, which is known as the angle of repose, which is like this sandhill here. When this goes past the angle of repose, meaning it becomes too steep, so if it becomes this steep instead, you'll actually have a slide. The sediments will slide down until it goes back to the angle of repose where it is stable. And then we have removal of vegetation. So, removal of vegetation is bad in many ways. It can lead to the steepening of sediment because there's nothing to really hold it down, so the angle of repose becomes smaller. There's nothing to keep sediment from being eroded away. Slumping can happen, and just plain old rock falls, okay? This can happen due to forest fires, deforestation, developing, farming, basically because people exist, except fire because that can be due to lightning or a random bear forgetting to put out his campfire. So the hydrologic cycle is not hydraulic, hydrologic, okay? So water moves between the ocean, the atmosphere, and the land, being the hydraulic cycle, also known as the water cycle, okay? So the hydrosphere, which we talked about in our first class, is where water is held. All the reservoirs that hold it, oceans, glaciers, groundwater, rivers, lakes, yes, the air, rock too holds water, I know, soil, and even living tissue. Okay, remember, we are water bags, because humans are just big water bags, and remember that when the aliens come and you'll be fine. So here's the hydraulic cycle, or hydrologic cycle. It should look pretty familiar. You should have seen this at least one time in your life ever. If not in high school, then at least in middle school. And I know that's a long time ago, but you know. So the hydrologic cycle is powered by the sun, solar power. So water will enter the atmosphere through evaporation, and there's more than one type of evaporation that occurs. You have general evaporation, which in this cycle shows it just coming from the ocean, but it can come from lakes and streams as well. But we also have evaporation or transpiration that occurs. Transpiration is when water comes out of plants. Okay. And then after it evaporates into the atmosphere, it will condense into clouds and then precipitate out as rain. Sometimes it will rain into the ocean, in which it's just a very small circle. Other times it will precipitate straight onto land or straight onto the mountains, and then it will have runoff, which is where we're going to get our rivers and streams, infiltration, which is when it goes into groundwater, okay, which then will come up in shallow aquifers or even as lakes where you have it dip really low. And then eventually this will all go out into the oceans, go back up into the atmosphere, and start all over again. So, we have these giant reservoirs that I mentioned earlier. Okay, we don't just have precipitation, evaporation, precipitation, evaporation. In colder regions, precipitation becomes a part of something called glaciers. So glaciers are those big frozen ice sheets. These are significant reservoirs. Melting all glaciers would cause some significant sea level rise, as in dozens of meters. To give you an idea, I am 5'4". You've seen me in class. I am exactly 1.6256 meters tall. So dozens of meters is like 12 plus of me. Okay? That's a lot. That is a lot of water. We would lose Florida. We would lose the coast of the east and west coast of the United States, as well as probably the rest of the world. So this is not necessarily something that's positive for us, not something we really want. I've said this once before in at least one of your classes, that in the Cold War, it was an idea of the United States in order to combat Russia was to melt the polar ice caps using nuclear energy. And this would have been a very, very bad idea. Very bad. And this is because of this having a sea level rise of dozens and dozens of meters, which they realized after, and then they were like, oh, maybe not. So yeah. Fun. So there is an annual average precipitation, which is the amount of water entering the atmosphere from evapotranspiration. Precipitation exceeds evaporation over land, but evaporation exceeds precipitation over the oceans. And this is everything I just said. So, running water. To give you an idea, in a forest, you have a lot of water being absorbed into the soil because it's used by trees, which means that there's always going to be free space in the soil for more water to go because the trees drink it up because they're thirsty and they're big and there's a lot of them because it's a forest. So, when you get a heavy enough rain, you get mud. And water will start to run off into local nearby streams and riverbeds. Okay. But this is particularly plausible in mountainous forests because then there's a lot of rocks or a lot of bedrock and less deep soil. In this instance, the water will actually run down rocks and into said things. In arid areas like a desert, surface material is a type of very fine-grained sand. Well, guess what? It doesn't absorb water very well. Water actually kind of bounces off. And this leads to some pretty insane runoffs, also known as flash floods. So in the desert, you have a very high chance of flash floods all the time, just because of how fine-grained the sand is. However, precipitation that runs off depends on all of these factors. So intensity and duration of rainfall, saturation percentage of the soil. Is it muddy already, or is it dry? Nature of the surface material, clay, sand, or soil. Soil is the most absorbent. Clay, it'll take a little while, but it will absorb it, and sand is the least absorbent. Slope of the land, extent and type of vegetation. Okay, is it forested? Is it just brush? Is it grasslands, or is it a desert? So precipitation runoff starts as unconfined sheets, which is where you get overland flow up here. Okay. This crosses hillsides and it will develop threads of currents known as rills, which will then go into deeper areas, which we call gullies. And these gullies will then drain down these hill slopes, which are known as into a drainage basin, which eventually goes into a stream or river. Okay, which will eventually make it to an outlet, and that outlet could be the ocean or a lake. Okay. The end point overall is the ocean. So even if it does go into a lake, that lake will have an outlet somewhere and it will eventually get to the ocean. So a drainage basin is an area that contributes water to a river system. Basins are separated by divides and these will vary in scale. So, for example, the Mississippi Drainage Basin. This is all the area that leads to the Mississippi River. Okay, these can be broken down into the Upper Mississippi Basin, Ohio River Basin, Tennessee River Basin, Arkansas Red-White, and the Missouri River Basin. And then each of these river basins can be further broken down into things like the Yellowstone River Drainage Basin. So it's kind of like they accumulate, like towns and counties and cities and states. So river systems will carry water from an entire drainage basin. Okay, and there's three zones. You have sediment production, which is where the most water and sediment is derived. It originates at what are called head regions, okay, or the headwater. Headwater regions are the start point. Okay, start. Right, then it will go to sediment transport, which is zone 2. Transportation occurs through the channel network via trunk streams, which are these. Trunk streams are sometimes what people call, oh, that's a lazy river. But this is pretty much what all of the Mississippi is. So this is zone 2. And then we have zone 3, which is the deposition zone. So deposition occurs when the river slows down. meaning that it doesn't have the energy to hold up all the sediment it has. This occurs when the river enters a new body of water where it will form a delta, and it can also occur as we get lazy areas of a river or trunk stream, but we're going to talk about that later. So stream flow characteristics are very important. There are two types. You have laminar and turbulent. So laminar is a slow-moving stream or lazy river, and that's a laminar flow. It's a fast-moving river will be known as a turbulent flow. And so to measure the turbulence in water is known as turbidity. Okay, so the turbidity of the water tells you how turbulent it is. So if you increase the velocity of the water, you will also increase the turbidity. Other difference between them is that it moves in a roughly straight line path parallel to a stream channel, but it doesn't necessarily increase its sediment load. A turbulent flow will lift sediment from a stream bed, okay, and they will also have rapids. And here is the difference between either. So in this one, this is a laminar flow. It's not standing still. It's just moving very slowly. And you can kind of see it here where it's hitting something that's in the water and going around it. Whereas this is a turbulent flow. And it happens to be in the rapids of the Grand Canyon. These are extreme. This isn't something you do unless you've had experience with whitewater rafting. Many people have died doing the whitewater rafting in the Grand Canyon. And that's just because of how extreme the rapids are. I think they're like a class 9, which is pretty high. So flow velocity is quite important for how a stream moves. Okay, the velocity of a stream, or how fast it's moving, will vary along a stream and through time. So maybe 5 years ago you went to a river and it was super turbulent, and then you go back today and it's gotten very calm. That's just something that naturally will occur. It will go up and down and up and down. This can be based on multiple things. It can be dependent on channel slope or gradient. So gradient is the vertical drop over a specified distance. This varies from stream to stream and over the area of a stream. So Niagara Falls doesn't have a drop like that anywhere else in the river, for example. The channel size and its cross-sectional slope and its roughness are also very important. So the shape and size and roughness of a channel will also affect the amount of friction between the channel and the water. The turbulence will cause a slower flow because of friction. So discharge is the amount of, or the water, or the volume of water that is flowing past a fixed point in a given unit of time. So it's given in meters cubed per second. And then we have intermittent streams, which only flow during the wet periods, so the rainy season. And we have ephemeral streams, which will carry water after a heavy rainfall only. So intermittent are seasonal, ephemeral are after a major downpour. So intermittent streams last longer periods of time than ephemeral. Okay, ephemeral streams will only be around due to large amounts of water, such as snowmelt or heavy rains. Once that water is gone, so is the stream, but the bed will remain, which shows you that it will come back with another heavy influx of water. So discharge, again, volume or amount of water flowing past a fixed point. Intermittent streams flow during wet periods, ephemeral streams only after heavy rainfall or snowmelt. So the longitudinal profile is the cross-section between, cross-sectional view of a stream from its headwater to its mouth. So it's start to finish. The shape is going to be a concave curve with local irregularities. Its gradient, sediment size, channel roughness will decrease from head to mouth, and discharge and channel size will increase. Flow velocity will also increase. So this is what a cross-section looks like. Generally, it's going to go straight down as its elevation decreases, but you're going to have some little changes along it. And this is from Mount Whitney in the Sierra Nevada as it goes to the Kings River, where it reaches generally a very flat plain. So as channel slope and channel roughness increase as it leaves the headwaters, its discharge also increases, but its channel size will increase slowly and its flow velocity kind of will increase as well. But channel slope, that's how steep it is, will decrease. Just as channel roughness decreases, it comes smoother. And that's because up here you're going to have all hard rock or bedrock, and down here it gets very soft. So what does running water do for this? So streams are an important erosional agent. Rain will knock sediment particles loose. The flow of the stream can dislodge and lift particles from the channel. Poorly consolidated material will actually erode much faster than consolidated material. And this will lead to undercut banks. And then hydraulic force can also cut bedrock. Yeah, it can erode the hardest stuff on the planet. This is enhanced by already eroded particles in the water, and pebbles can actually carve potholes in the channel floor as turbulent waters swirl them around. So raindrops can strike the surface of the earth at velocities approaching 35 kilometers per hour. When a drop strikes an exposed surface, soil particles can splash as high as 1 meter and land more than a meter away from the point of the raindrop impact. If you've ever been at a beach or just outside when it rains, sometimes the backs of your legs get all sandy because of raindrops doing this. The rivers that have muddy appearances, like this one, is actually due to suspended load, meaning it has a lot of sediment that it's carrying, which means it has enough energy to actually carry this much. So these are the potholes that I was telling you about pebbles getting swirled around. It's known as abrasion, and it's long-lived whirlpools armed with pebbles, creating bowl-shaped depressions in bedrock. So how do streams transport the sediment? We saw over here, for example, the river's muddy because of suspended load, but how does this happen? What is it exactly? So we have three types of load. We have dissolved load, which is when there's material in solution, such as salt water, it's got sodium in it already, or mineral water. Okay, these are all dissolved loads. And you can't see these dissolved loads because they're invisible, because they're already suspended within, such as sodium chloride. When the water evaporates, the dissolved load will actually come out in the form of salts or other minerals. Suspended load is a bit heavier. You can actually see it or feel it. This is usually delivered by groundwater, and it's not affected by the water's velocity at all. This is going to be things like silt or clay. Sometimes sand, very, very fine sand, which turns into silt at that point. And then we have bed load. Bed load is the material that moves along only the channel bed, hence bed load. This is where we're going to see larger particles being moved during floods or when there is more stream energy. So bed load is going to be heavier material such as gravel, boulders, and sand. Sand can sometimes be suspended depending on how much energy it has, but most of the time they move by something called saltation, which is bouncing as well as sliding and rolling. Suspended load is the largest component of stream load. The bed load is the material that moves only along the channel bed, and it has to have enough energy to move it. This isn't permanent motion. It'll only be moving when there's enough energy. Smaller particles will move via saltation, and larger particles will move via sliding and rolling. So stream channels is where stream flow occurs. So you have two types of channels. You have bedrock channels. These are cut into solid rock or bedrock. They're common in headwaters where you're going to have a steep gradient because, again, most headwaters or start points are at the top of mountain slopes or hill slopes. These will transport coarse particles, And you'll see an alternation between gentle and steep gradients. So you'll see a difference between alluvial channels and bedrock channels. And alluvial channels are composed of unconsolidated sediment, where you're going to have your softer ones. These are going to erode much faster. So channel pattern is controlled by the underlying geologic structure of the area, meaning the water will cut through softer bedrock faster, leading to winding and irregular stream patterns, because nature likes to go the easy way, like everybody. So if over here is easier to cut through than this direction, we're going to go the direction of least resistance. So you're going to find riverbeds like this one, or these ones, along the east and west coast in mountainous areas like the Rocky Mountains. Okay, this has to do with the fact that the east coast in particular, like New England, is primarily bedrock because it's very mountainous. You'll also get things like these, which are very pretty. I love going to waterfalls. Alluvial channels are composed again of loosely consolidated sediment. These are continuously being eroded, transported, and then redeposited. The shape of the channel is controlled by the average sediment size, the gradient, and the discharge. So two common types of these types of channel are meandering streams and braided streams. Meandering channels tend to have these big sweeping bends called meanders. These have high suspended loads, meaning that they generally look pretty muddy, deep, smooth channels, and erosion-resistant banks. Basically, the Mississippi River. So most of the erosion will occur on the outsides of the meander or the cut bank, which is this part right here. This is where velocity will be the highest. Okay, so if we were to look at a stream bed like this, when the stream is going straight, its highest velocity is going to be here. And when we are going around a curve, its velocity will actually shift towards the cut bank, which is the highest resistance, right? Meaning that we become very slow on this side, which is where our deposition is going to occur. And that's what your point bar is. This is all deposition, because that's where it's slowest, that's where the energy is least, that's where sediment's going to be deposited. And this leads to the movement of the meander outwards, like this. So eventually your meandering stream, which originally may have looked like this, will turn into something like this. Okay, and then as you get points like this that are very close, these will actually connect because it'll become easier to do this and go back to something similar to that. Okay, this all depends on energy of the stream. Okay, how much water is moving through it. So again, meanders migrate laterally and downstream, all at the same time. So they can actually cut off, which will form an oxbow lake. And these oxbows eventually will dry up and they become what are known as meander scars. Okay, then we have something called a yazoo stream. So a yazoo stream is a stream that runs parallel to the meandering stream. It just doesn't have a way to join the stream yet. Eventually, it will find a way to join in with our meandering stream, becoming part of it. Okay, so it is a tributary. It tends to run on the floodplain because these meandering streams do flood periodically. And that's what these bluffs are. These are the edges of the floodplain. And usually when we have floods happening, maybe this yazoo stream will eventually find its way entering the meander, or just further down it will enter. But generally what happens is once the floods recede, you'll end up with water that gets stuck, and this is known as a back swamp. And part of this is because as the water overflows over time, which we'll see here, it will actually build up sediment along its edges. So you'll have, over time, the build up of what we call natural levees. Okay, so remember that your stream velocity does change with where exactly it is. So when it is going straight, your highest point of velocity will be in the middle. When we are going around a bend like this, your highest velocity point will move to that point bar bend where the erosion is happening, okay, which leads to deposition on the opposite side, okay? So think of a car going very fast around the curve, it will drift. So braided streams, on the other hand, are a stream that has variable flow. So you're going to start out with a large amount of discharge, which will allow it to pick up this easily erodible material, such as on the edge of glaciers, which will be essentially glacial runoff. And what happens is it's kind of like carrying this big pile of books, okay? You start out being able to carry, let's say, 20 books, you have all this energy, and then as you're carrying these books down the hall, you're realizing you can't carry all the books anymore. So you start dropping books until you get to a load you can manage, and then once that gets to be too much, you start dropping that. And that's essentially what happens with these streams, is they have this huge amount of sediment that they've picked up when they had all this energy from being a very large output of water. And as that output of water decreases, it can no longer carry the same load, so it starts to drop it, essentially like as these little islands of sediment. And so what happens is once you get a larger flow of water coming through again, this sediment will then be picked back up, and then it will be deposited further downstream as it runs out of energy again. And so that's how braiding works. So it creates this complex network of converging and diverging streams, but it is all one river. So it's pretty neat. It is kind of cool to see in person. So this is most common at the edges of glaciers. And that's the end of part 1 for mass wasting and water movement. We will pick this up in our next lecture, and I hope you have a great day, and I'll see you guys later.